Thank you, Kalle. I would like to thank the organizer for inviting me to come here. It's very interesting. I also must say that the previous speaker, it was really interesting to see that the company in that kind of business is very aggressive, so to speak. Because I will talk about industrial automation, and I should say that you probably will see me as a guy that comes from Jurassic Park. And it's also important, I think, for other industries that try to enter and take market shares in industrial automation to know this is a very conservative industry. Typically what happens is that if you're going to try something, the new technology, you try it on a very limited scale, it should run for a couple of years, then you extend it, and then maybe after some more years, you call your colleague that has a factory in Britain and said, hey, this new technology, it's rather good, you should try it. So it's not like a cell phone, you throw it away after 1 year and new stuff comes. So, I don't know how familiar you are with industrial automation, but nowadays there are a lot of companies like SAP, IBM, and also telecom vendors try to enter this market. There's a lot of white papers coming, and everyone is saying it's automation. I think that we should be careful, and it's also good to know if you're going to talk with these guys, you should use the right terminology. And typically, industrial automation is divided into a few sub-areas. We have process automation, typical oil, gas, chemistry, have a different set of requirements. We have discrete automation, factory automation, car factory manufacturers belongs to this. And we have substation automation, which basically is a subset of power networks automation, which has really tough requirements. And then I would say we have these softer industrial applications, building automation, home automation. I wouldn't say it's not too challenging requirements. You can solve it pretty easy. And then someone might say, okay, what about HVAC? If there's a fire, you want the fire alarm to go quickly and so on. But I mean, it's still quite relaxed requirements on these kind of applications. So just to give you a hint of the numbers from different application domain. If we talk about process automation, it's typically an update rate between 10 to a couple of seconds, and there isn't too much sensor nodes per square meter. They are typically distributed over a very large area. Then we move to factory automation. We are talking about update rates from 50 microseconds to 100 milliseconds. Now it starts to go a little bit faster here. And the density is much more. Also, there could be 100 sensors in a square meter, for instance. Also quite challenging requirements. Then we come to substation automation. You can see the numbers. And then we have high voltage DC control. The numbers are extremely tough. And I typically say you should also be aware of these numbers include processing time for crypto and so on. So there is a reason why we're using fiber optics, for instance, for high voltage DC. And I also heard that some researchers are thinking of using cellular communication for substation automation, controlling, balancing the control loops, these kind of things. I think that's little bit too sky blue if you're asking me. But probably we can discuss it later. So what are the basic properties then when we're talking about industrial automation? The most important is safety and security. Safety is the most important property whatsoever, personal safety. And also safety that your machinery and these kind of things, I mean, there's a lot of investment there. So it's extremely important property. High availability, redundant protocols, extremely important. Then we have deterministic communication. It's important that the data actually comes when it should come. Even if it's a very slow application, let's say that I want my data come at 1 o'clock every day. It should not come 12:59 or 1 second after 1. It should come at 1 o'clock sharp. Otherwise, there's a production failure. Low latency and jitter. And of course, efficient deployment, maintenance, flexible topologies, and on top of that, high throughput. This is very contradicting requirements. It's not that easy to design one single system handling this properties then. So what are the grand challenges then for automation if we're looking today? Of course, it's to get the 100% available plant. And that production stop should be perfectly planned, and we want to have more embedded devices into the production so we can improve the quality of the products and so on. What we also see, as the former speaker said, about energy efficient equipment. I mean, the device is typically from the end customer. If you have a wireless sensor node that measures temperature or something like that, the requirement, it should last for 5 years at least. And then it depends, okay, but if I need to sample every second, we have a challenge here, that this battery should remain for 5 years. And another problem also when it comes to batteries, they need to be standardized. You can't just say to the customer, okay, you need to have 5 different brands on stock. And you probably also need to hire 1 or 2 guys to go there every day, exchange batteries in a very large plant. And then we have this, that wireless communication is start to coming into the process automation or automation, and it will come even more. But it needs to be secure. If you're talking to the end customers, okay, why don't you use a wireless technology? It's not secure enough. When you can ensure me that this solution is 100% secure, I will buy your system. That's what the customers are telling you. So what's the next challenge we have? It's about complexity. You need to hide the complexity for the end user. Today we see that all new products become more and more complex. When you're going to deploy it in a plant, you more or less need a PhD to do this. So I think this is something that we really need to take seriously. We need to hide the complexity. And also if in a control room, I mean, many researchers thinks that operator, he or she wants to see everything, want to see the bit error probability, these kind of things. They don't care. They want to see red or green light. Is my link working properly or not? If not, I need an alarm. They don't care if they can see latency, these kind of things. Simplicity is the key word here. But it's very difficult to do it with all the new technology that's coming. So that's a little bit of the grand challenges. So what's happening then in the community to achieve these grand, or taking care of these grand challenges we have? And a lot of discussion today in the society is digitalization. For all the government, everything. This is a keyword. This will transform the industry. And I think we should be careful here, because the automation business has been digitized since 1970s. With PLCs, control system, everything has been digitized. So let us not confuse this. So this is a real myth, I would say. This has already happened, more or less. Then we have another myth here, is that Industry 4.0 is the 4th industrial revolution. There's a lot of discussion with this, a lot of money going in here. And I would like to say, it's not the new technology. This is basically, we didn't have the technology to do this before. But over the years, new stuff have come, and now we can actually start realizing. What I think, from my point of view, what Industrial 4.0 is more about business model. How to create new values for the companies. And what is also needed to make Industrial 4.0 is you need skilled workforce. You need people with a good computer science education, because there will be a lot of big data, these kind of things. You need to know how to handle it, process it, and interpret it to make good decisions. Then, of course, Internet of Things, cyber-physical system is a lot of talk about. And to cite one of the corporate research fellow within ABB that has been working with communication for 30 years, when he first heard the term cyber-physical systems, his comment was, oh, in 1990s, we called it distributed systems. So I would say it's quite funny. It's the first time that actually an industrial revolution is announced prior to its occurrence. And as I see Industrial 4.0, it's more of an evolution. It's not a revolution here. And then if we have the industrial Internet of Things, we also, which is a part of the Industry 4.0. A lot of people talking about 6LoWPAN, IoT, that will be the game changer. I'm not so sure, because IP actually introduces a lot of problems. And if we have real-time control, short delays, these kind of things, and since most of these networks today are run on sensor networks, 802.15.4, packet sizes of 128 bits, you should defragment a large IP packet and these kind of things. So, a little bit concerned about it. And it will for sure not solve the problem with deterministic communication in that sense. Other key challenges we have device capabilities. And it's important to realize here, as also the former speaker said, that it's not just bringing some from the IT world, put it into the industrial context and think it will work properly. In certain environments, you might have 50, 60 degrees Celsius. Okay, will the device work properly? If you are really unlucky, the oscillator starts to get a little bit shaky, and then you're out of sync, and then you run into a lot of problems. Security is probably the big major problem, especially if you talk to the customers. And they said, why should I actually be able to ping my sensor device? What are the business value for me by having it on IP? They don't see the business value of running IP. Then the question also come this morning, safety is extremely important. Then standardization is also of high importance here. These kind of industries, they seldom buy proprietary system. It should be standardized systems. And then there's also a lot of talk about this big data. And I can basically say, yes, it's partly a way to our success. But to cite one of the guys, Mike Williams, working at Dow Chemicals, for those who know about the company, they have like 250 plants around the world. Big data, been there, done that. And you can see Facebook, for instance, had 1 billion transactions per day. In a typical chemical, oil, gas company, you have 2.6 billion transactions per day. The main problem these guys facing is that they have so much data, but they don't know what to do with it. So they need some smart algorithms so they can actually improve the products or give the customer more value, so to speak. So that is also important to know. So then if we then go to the more funny stuff, because we're here to talk a little bit about wireless. So why should I use wireless for industrial automation? What are the arguments here? First of all, I would say we are able to measure on places we couldn't do before. Could be on rotating things, for instance, or it also offers a lot of flexibility, ease of maintenance, but then we need to recall we can't make the stuff too complex, because then there will not be ease of maintenance anymore. So then if we look at the typical plant, what kind of wireless technologies do you find there? And then we should start within an automation business. You typically have 4 layers. You have a plant network, that is where the CEO sits, reads his email and these kind of things. We have the server network, here is the operator sitting, watching. We have the control network and we have the field network. Typically on the field network, this is where I will continue discussion later, is typically we are running wireless sensor networks. And you can also find Wi-Fi. That's typically the wireless technologies you will find there. Then if you move higher up, you will have GPRS, 3G, these kind of things running. And an oil rig is a little bit special. Can anyone guess how many communication systems typically an oil rig has? It's roughly around 30, 35 different systems you need to maintain and running. So if you then look into especially the process automation, I will stick with the process automation right now and leave out factory automation and substation automation. The main standards that are running today, they're based on the wireless sensor network standard IEEE 802.15.4. There are 3 main standards. It's wireless HART, it's ISA 100, and we have a Chinese standard called WIPA. And these are the 3 that you will find and you need to cope with, so to speak. And they are evolving a little bit when they find certain of diseases, so to speak, on the technology in that sense. So what basically are these problems with these standards? I mean, everything is not working perfectly. We need to admit that one. And we should know that typically we have different classification of applications. The current wireless sensor networks that actually comes from the consumer market, they didn't think about you should control something. It's only monitoring, bring in data. And so they actually manage the classification of monitoring. Then the company said, okay, would be fun if we could have some flow control. So these standards that exist today, they can actually manage, I would say, slow wireless control. And the main difference between if you take a Zigbee device or a wireless HART standard or a ISA 100 is that they also use TDMA. So they get rid of this contention using CSMA CA. And they also using frequency hopping. So they have added some fancy stuff so to make it a little bit more reliable in that sense. And now the community start talking about, okay, but we need to address safety and more fast control loops. And I think if we're looking into 5G, you're also using this classification. I think your massive MTC, whatever you call it, you're targeting these 2, if I'm right. So it's good that you're using this picture to communicate anyway. So what are the main challenges then? And of course, it's a harsh RF environment. It's extremely difficult. It should be mentioned that these standards work on 2.4 gigahertz also. So, I mean, you also have a competition from Wi-Fi, Bluetooth, other devices. And you can't say that all sites looks the same. You can have let's say a paper machine. It's, as you see, here it's very compact. Here it's open spaces. You go to another factory, you have a lot of pipes. So you can basically benefit from a little bit of multipath and these kind of things. And if you go then to a paper warehouse, basically all signals are sucked up by paper. So you don't gain anything. So if you have no line of sight, I mean, you're screwed in that sense. So this is a very challenging for designing the wireless system in that sense. And of course, as I said, you have interference from other devices, and you actually could, in some production sites, have from micro ovens, and they kill the complete ISM band. And if you then have a real-time communication and a really safety critical application, you're in a serious problem here. But then one could maybe ask, okay, what happens if I go down in frequencies? I don't have all these devices. That's true. But then you have a problem from the EMC problems, because different devices actually gives away disturbances. You can even get spikes of disturbance from arch welding up to 1 gigahertz. So then you have that kind of problem you need to take care of. And if you go up to 5 gigahertz, well, then you have the Wi-Fi once again. So this is actually some measurements we have done a couple of years ago. It was actually a Vinnova-funded project together with KTH and Uppsala. And this RF measurements was actually only Uppsala that was involved in. But nevertheless, this actually shows a picture from Iggesund paper mill. And what you can see from the picture there, was 24 hours of measurement. It's a very stable radio environment. But we had a problem anyway. That you see these paper rolls, this should be clean. But there was actually a problem in the end on the production line, because where you cut these paper rolls in pieces was broken. So during the night, they need to lift out these paper rolls to be able to continue to produce paper. But if you then have a critical communication, this happens. This is nothing you plan for. And these paper rolls killed the communication when we deployed 20 sensor nodes. Totally killed the communication. And that's why mesh networks are nice, because then you can reroute. If you have a star network, sorry. And then we actually went to Boliden, the Garpenberg mine, and the tumbling mills. And there you can see a completely different radio environment. A lot of Rayleigh fading. So by that I would like to say it's very difficult to design a system that fits these kind of processes in industries. And I think it's also important from a research point of view that we do more experiments and measurements to learn to design a good wireless system. And then we have the effect of interference. This is something we did when I was working at ABB. We had a system running, no Wi-Fi, and suddenly we turn on the Wi-Fi, and you can see how the latency is going exponentially. Actually, from up to 250 seconds before the packet arrives, you can't have a system running like this. And then on the other one, we have it on another floor. Of course, the interference was less, but still it's a problem. So this is something that needs to be taken care of. And well, there are different ways of doing this with interference awareness. I will not go into details. You can do packet inspection, use some kind of steal methods from spectrum sensing, these kind of things, and try to implement. And what I would like to say, what's more important and difficult here is that the sensor networks, they come from the chip manufacturers, and you don't have access to do anything. It's a black box. The only thing you can do if you're a vendor like Ericsson, Siemens, Emerson, whatever, you need to do it on top, on the physical layer, so to speak. So that also gives you very little freedom to add the features to combat interference and so on. So the next challenge is real-time system constraints. I think this is important. Communication reliability with the 5 nines. That means you have 0.86 seconds of downtime per day. This is a requirement. Otherwise, it costs money to have the production stop. The production stop in a paper mill, 1 hour, costs you 300,000 Swedish crowns. Which sounds very little, but I mean, typically a production stop is 5-6 hours. So then we add up and the CEO starts screaming a little bit for you. Anyway, another thing is strict timing requirements. As I said, we're talking real time here. It's hard real-time systems, mainly. You should always design for the worst case delay. I mean, average delay is no interest. You see so many papers from researchers, and they have average delay as a performance measure. It doesn't tell you anything. It's a worst case delay that is of interest. Retransmission may cause network congestion. One can also discuss, is it important to send the same message five times, retransmit? Because why don't you take a new value, send that one, because then you get the fresh value. Of course, it could be nice with statistics afterwards to look, but I would say take a new value and submit that one instead of try to retransmit. And for the sensor networks that working today, they have no forward error correcting capability whatsoever, which it's crazy. And then you may ask, okay, why? And I think it was a design choice. It was basically energy consumption. It took too much energy to do the encoding, decoding. But on the other hand, you can then discuss, it also costs you energy to fire up the radio. Then we come to the timeliness. And this is the major problem today with the sensor networks. They are built on CSMA, CA. You have the same problem for Wi-Fi today. And that is, we have random backoff. The delay is not deterministic. So what is really needed for a future wireless sensor network, I would say, that is a new MAC protocol and deterministic communication. That is really what is needed. And of course, then we have routing, real-time communication. This is also a problem. And it will become even more important when we're running wireless control applications. I know Kalle has run a few projects looking into this, and which has been quite interesting results. Although I think we need to do more here and also do more field trials to really learn and gain experience about this. There are also some other problem is that, okay, how do you incorporate emergency events in the communication here? Should you schedule it already from the beginning? That means your channel utilization will actually be less. So that becomes a problem then. So I will have 2 slides more, then we come to 5G. Then maybe I've challenged you a little bit or not. I basically see there's a lot to talk about this 1 millisecond delay. And my question is, what kind of applications need 1 millisecond delay? And is there a business case for that one? So you need to design a system for maybe 2 or 3 use cases where you maybe sell 10,000 components. Probably not. I would say go where the money is. Another challenge is where to get the spectrum for this one. And then, of course, there's a business model. Who owns the network? I think that should it be the plant owner or should it be the operator? Who should own it? How should I pay for it? And is the client willing to pay for availability of the information exchange, for instance? These are a lot of open issues. And I think this is something that really needs to be considered. Cost of the devices. As we said before, a lot of these devices need to be IP classed. If it's going to sit on an oil rig, they need to be ATIC certified. The cost going exponential. And it's serious, this one, with the cost for devices. Then we have this with the standardization. I know that there's an ongoing process this standardization. But if you then recall 4G, it took 10 years. Probably you will say, no, your fault. But nevertheless, before these systems are standardized, there's a lot of systems that will be deployed. And we should also recall that these companies, they require backwards compatibility with their installed base. So if there's 100,000 or 10 million devices, you need to ensure your system is backward compatible with installed base. You don't throw out investments for a couple of $1 billion. And I also think this is crucial, that it's important to involve the automation companies into the standardization to you and the end users, so you really get to know the real requirements that they are asking for. And of course, a lot of technology challenges, radio environment, latency, reliability, batteries lifetime of 10 years. We should recall batteries themselves are not reliable. They self-discharge. And so that's basically some of the key challenges I see with 5G worth considering. There are plenty of others, I would guess. So just some concluding remark. I would say Industry 4.0 is not a revolution, it's an evolution. Key challenges for wireless communication, if we just only consider process automation, is the spectrum issues with coexistence, these kind of things. It should be also mentioned that there are companies that driving on ETSI level that all devices in 2.4 gigahertz should actually work like Wi-Fi. So if you have a time-critical process and your product is running Bluetooth, you're in a problem. So there are companies actually driving this on ETSI level, that all devices should occur as a Wi-Fi. Battery lifetime, and I think that we will see Wi-Fi sensor networks the next 5-10 years dominating the field bus level. And I think that 5G will probably play a central role, but I think maybe not in certain domains within industrial automation. So that's all.
Okay, thank you very much. Questions, Mikael? Yes.
Thank you. Yeah, interesting. I had just one actually a comment. You didn't mention it that much, but on the new technologies, on your previous slide, you had the nice picture of a massive MIMO antenna from Lund University.
Yes.
I happen to be part of designing that antenna. I would just make a promotion of 5G for that, because that antenna is on the base station side in order to reduce the devices with the antennas and improve the link. I think you didn't talk about it.
No, I didn't talk, and I'm fully sure that it will not be deployed on the devices. But I think
your text was as I was.
Okay. Then you interpreted it wrong then. But I think it's still a challenge, because I think one thing that one should remember, that in these kind of environments, you cannot just place the devices wherever you want them. No. They need to sit on certain places, and that's probably not the best radio environment you can do. Even if you do this kind of radio service, it needs to be there, and it's probably the worst place on the factory, so that you need to cope with. So I think size still matters in that sense. So
that was just a comment. Thanks for the interesting topic.
Thank you. Good. We have a careful audience taking the slides. Claes, you had a...
You talked a little bit about installed base, and as I said to Peter also, there's a lot of installed base in Swedish industry, and I know that just this small company Åkerströms, they have an installed base of about 20,000 radio systems for remote control in Sweden, and they are predominantly operating in the 433 megahertz band, and there are several reasons for that. But you didn't include those type of installations in the 433 megahertz band, and I also never see 433 megahertz in the discussions around 5G.
No, the reason is, I know there's a lot of system working on both 433, 866, but since the standard for process automation, they entirely run on 2.4, because that's internationally, there's a lot of COTS devices there. I mean, it's a volume. Everything is about volume here. So you can't come and say, hey, I want this feature, and then Texas say, okay, what's your volume? It's 100,000. They just laugh at you. Okay, come back when you have quadruple that number or something like that.
Okay, James, next question.
Yes, maybe more as a comment. So I heard talks from automation industry a couple of times that we're going in the same direction as you were also now advocating it. So if you look into wireless technology that is commercially available today and that is also deployed shop floor, this is typically state of the art 20 years ago from a research perspective.
Yeah.
Okay, so for most questions that you're coming up with here in this talk from a technological point of view, there are solutions. Okay, I agree. It is an issue of bringing it down to a commercial platform. And this is a cost issue and this is a spectrum issue. Yeah. But it's not so, let's say, the situation is not so futile as you're posing it here, okay? Or as I perceive it, at least from your talk. So just a comment. Okay,
okay. Last question from Jens here in the front.
I have a question about sort of the reasoning in the factory automation business. About you mentioned that the cost of devices is very high because they need to be certified and tested. And I see in the old days when I was sort of in the military domain, I mean, we have military specified equipment, and the reason was that you have a sort of a single point of failure philosophy, so every device has to withstand a nuclear attack or something like that. So it's extremely overspecified, because so you want 99.99 because you have a chain of devices that together form a single point of failure chain. Where I think today you probably have sensors, a multitude of sensors. Another strategy is to deploy a lot of sensors. So even if they fail, they always have enough information to detect the difficult and hazardous event that you want to protect against. So it may be, you see some change in philosophy there, that you look at more system reliability rather than individual device reliability, which drives the cost on the devices.
Of course, first of all, I think it should be mentioned that all devices do not need this rigorous IP protection. It depends where they are located. I mean, there's a big difference to deploy sensor network, let's say, on an oil rig compared to go to a paper machine or paper factory in, let's say, in Sundsvall. I mean, so the devices are already there, cheaper, because you don't need to do EX proof and EP protection, these kind of things. So, but I think you're right that it will probably in the long run start to think more on the system level, not on individual device level. But I think this is also a mindset at the companies that, I mean, when IT comes, they meet the instrumentation engineers. They don't have the same mindset. So I think it's also a culture from the companies that needs to be changed to overcome this hurdle when it comes to adopting new technology. It's not only technology, it's also about mindset and the people, skills and knowledge that needs to be changed.
Okay, thank you very much. Let's thank the speaker again.